The question that I have is, could you explain the principle of moments? Let's say I have a force F acting like shown in this picture. I want to find the moment of this force about point O. So one method would be to simply work from the very basic definition of moment, right? So what do? Well, we extend the vector representing the force in order to establish the line of action, right? And then we draw a perpendicular from point O to the line of action. Find the distance from point O to this point where the perpendicular intersects the line of action. So in this particular case, it's a little d, right? The force F is going to rotate the point O in the counterclockwise direction. So I have a positive moment, and the magnitude of the moment is force multiplied by this perpendicular distance, d, right? So F times d. So this is still a scalar method. We are not talking about any vectors here, right? All of these are scalars, right? So it turns out there's one more scalar method, and this method is based on the principle of moments. The principle of moments states that the moment of a force about a point is equal to the sum of the moments of the components of the force about the point. So to implement this principle, we follow these steps. First, we go ahead and define a two-dimensional Cartesian XY coordinate system. So this is the system that I'm going to use here. Next, you want to take this force and resolve this into two components, one along the x-axis and the other along the y-axis. So in this particular case, if I call this angle as theta, my x component is f cosine theta, and my y component is f sine theta. Our third step is to simply sum the moment of each of the components in accordance with a sign convention. So here, this is our sign convention. Counterclockwise moment is positive, right? So we have two forces now. So we forget about the original force F. So this F has been now replaced by these two components, right? So now we got two forces, right? So F sine theta has a perpendicular distance of A. Why? Because this is the line of action of that, right? And from point O, the perpendicular distance to the line of action is this, which is exactly equal to A. And this is a counterclockwise moment, and therefore I have a positive sign in front of that. Now we take the x component, which is f cosine theta, right? And the perpendicular distance to that is b. Why? Because this is the line of action, and this is the perpendicular distance, and that is b. All right, so f cosine theta multiplied by b, but this time we have a clockwise moment. F cosine theta represents a clockwise moment, so we introduce a negative sign there. That's it. So the principle of moments says that this is exactly equal to this. All right, well, whatever we got here is supposed to be exactly equal to this. So it's not obvious, so let's prove it. So to prove this, I drew a couple of construction lines here. This line is drawn to be parallel to this, and therefore both of these lines will intersect this line of action at 90 degrees, right? Now I'm drawing this line to be parallel to the line of action, and therefore this angle is also 90 degrees. Now we recognize that if this is theta, right? And this angle will be 90 minus theta, and therefore this angle will be theta. Now considering this triangle, right? This side is A, this is theta, and therefore this must be A sine theta, right? This is A sine theta. Now you come back and consider this little triangle. This is B, this is theta, and therefore this must be B cosine theta. So if I take this, which is A sine theta, and subtract B cosine theta, that should be equal to this distance, right? Which is exactly equal to D. And that's what I have over here. So alright, so having obtained this relation, let's go back to the equation we got in the earlier slide. Alright, so this is what we had, right? This is based on the principle of moments, right? Now we see F in both terms, so I'm going to pull that out. And within the parenthesis, I have A sine theta from the first term minus B cosine theta from the second term. Now we recognize that this is exactly equal to this, right? And therefore this term is simply equal to d. And therefore, we have proved that the principle of moments, which utilizes components of a force to obtain the moment, leads to the same result that we got by the straightforward application of the definition of moments. So now we got two ways to evaluate a moment about a point, moment of a force about a point, when the force is not parallel to one of the coordinate axes, right? So you can still use the definition, which is force multiplied by the perpendicular distance, the line of action. So if that is still easy to do, you could still use that method in order to find the moment. If that is difficult, in many cases that is the case. It is kind of difficult to find the perpendicular distance. So if that is difficult, then you might find this method, the method based on the principle of moments, to be easier than the straightforward application of the definition. So keep in mind, you got two methods. Look at the problem and see which one will work better. Most of the time, this method will work better.